Hi students, in this session we are going to discuss about the topic Fourier transforms of a different types of signals like arbitrary signal, a standard signals, a period signals. So we have different types of signals. For all these we have to find out the Fourier transform. Okay, or simply you can say we have to find out the Fourier transform of some basic functions. In that, the first one is unit impulse function. Unit impulse function. Unit impulse function. Okay. So for this unit impulse function, we have to find out the Fourier transform. To find out the Fourier transform, first we have to know what is an impulse function. We all know the definition for impulse function. That is, the unit impulse function is first represented with del of t, and the del of t value will be equal to 1 for t equal to 0, and this del of t equal to 0 for t not equal to 0. Simply here they are given the function as unit impulse function, and the unit impulse function is represented with del of t. Okay, this del of t is having only two values, that is 1 and 0, and this del of t is having a value 1 at t equal to 0. So whenever the t value is 0, that is del of 0 value is 1. For all the remaining values of t, except 0, that means 1, 5, 15, 45, whatever it may be, whatever the value of the t, del of that value will be equal to 0, because the unit impulse function exists only at t equal to 0, and that value will also equal to 1. So for all the remaining values of the t, the value of this unit impulse function is 0. This is unit impulse function. For this, we have to find out the Fourier transform. So to find the Fourier transform, first I need a formula for finding the Fourier transform of a signal x of t. So what is the formula for finding the Fourier transform of a signal x of t? The Fourier transform is represented with x of omega. Now the value of this x of omega will be equal to integral minus infinity to infinity x of t e power minus j omega t dt. So this is the formula for finding the Fourier transform of a signal x of t. The signal x of t is given. For that, if you want to find out the Fourier transform, then the formula is x of omega equal to integral minus infinity x of t e power minus j omega t dt, where x of omega is the Fourier transform of x of t. Okay, so this is the formula for signal x of t. Here the given signal is unit impulse function. The given signal is unit impulse function. That is, the given x of t is nothing but our del of t. So here x of t is nothing but our del of t. So given signal is unit impulse function. So for that I have to find out the Fourier transform. So the x of omega will become as, now x of omega, the Fourier transform of this function will be equal to integral minus infinity to infinity. Now the function is unit impulse function, that is, in place of x of t I have to write del of t e power minus j omega t dt. Clear? Now see, the limits are from minus infinity to plus infinity, that is minus 1000, minus 900, minus 5, minus 4, minus 3, and 0, 1, 2, 3, 4, 500, 1000, 10,000, and up to infinity. So there are infinite number of values. Here the del of t exists only for t is equal to 0, and that value is also equal to 1. So in all these values, we have the value of del of t only at t equal to 0. So I will left all the values except t equal to 0. So I have to consider only t equal to 0. So okay, I have to consider del of 0, because in all these limits the unit impulse function exists only for t equal to 0. For all the remaining cases, the value of this one is 0. 0 into anything is 0. Integral of 0 is 0. So no need to take all the remaining values. So here we need to take only the value of t equal to 0. So del of 0 into e power minus j. In place of t, I have to write 0. I have to write 0. I have to consider only that value because this del of t exists only at t equal to 0. This is one way of representing. Or you can represent this. Or you can represent this like this also. Simply, this is existing only at t equal to 0. Or simply you can write this function e power minus j omega t exists only at t equal to 0. Okay, that is t equal to 0. So that will be equal to, so you can write like this, or you can write like this, whichever is a better understandable to you, follow that way. Okay, so for both answers, substitute t equal to 0 here. Substitute t equal to 0. What happens? E power minus j omega into 0. Here, del of 0 equal to 1. 1 into e power minus j omega naught. E power minus j omega naught. So what happens? So 1 into e power minus j omega into 0. Anything into 0 is nothing but 0. So that will be equal to 1 into e power 0. That will be equal to 1 into 1, or simply 1. Okay. So for unit impulse function, the Fourier transform value is equal to 1. So how can you write that one? How can you write? So I need the Fourier transform of del of t. So this is how to denote the Fourier transform of del of t. So in this way I can denote Fourier transform of del of t. That will be equal to, what is the Fourier transform of del of t? 1. That is nothing but 1. Okay, in this way you can represent. Now here this del of t and the 1 will form a Fourier transform pair. This del of t and 1 will form a Fourier transform pair. So how can you represent the Fourier transform pair? That is, this del of t will have a Fourier transform as 1. So for this I can represent like this, or I can denote like this. So both are same. This is one type of representation. That is, del of t is having a Fourier transform 1, or is another type of representation. That is, Fourier transform of del of t is nothing but 1. Both are same. Clear? So finally what you got? I got the value of x of omega equal to 1. For this I can draw the magnitude spectrum and phase spectrum. So how can we draw the magnitude spectrum and phase spectrum for this one? Simply, for a complex function has both a real part and imaginary part. Here, see, here we have only real part. That means imaginary is 0. So for this x of omega, first I need a magnitude. Magnitude means mod of x of omega. Nothing but square root of a real square plus imaginary square. There is no imaginary part. Leave it. So square root of a real square. So real part is 1. Square root of 1 square. Nothing but 1. So this is the 1. Magnitude of this one is 1. Okay. For all omega. Okay. In the same way, what is the angle, phase angle of this x of omega? Formula is tan inverse of imaginary by real part. So there is no imaginary 0. So tan inverse of 0 by 1, that is 0. So tan inverse of 0, simply the answer will be equal to 0 for all omega. So this is the magnitude value, this is the phase value. Now we have to draw the graphs. First I will draw the magnitude spectrum. So magnitude spectrum is nothing but a plot of frequency omega versus magnitude. So see here, on x-axis I have to consider the value omega. Okay, on y-axis I have to consider the magnitude of that value, that is mod of x of omega, mod of x of omega. So for all values of omega, the mod of x of omega is 1. So let us consider this value is 1. So for all values of omega, the function will be like this. So this value is equal to 1. Okay, this value will be equal to 1. Clear? This is the simply magnitude spectrum. Magnitude spectrum of the given unit impulse function. In the same way, I can draw the phase spectrum also. The phase value is 0 for all values of omega. So how will you draw the graph? So this is omega, and here this is the phase, that is angle x of omega, phase angle. So for all values of omega, the phase angle will be equal to 0. So this is 0. This is 0. Okay. Here it is 0. There is no graph for that one. So this is nothing but the phase representation. This is nothing but the phase spectrum. This is nothing but the phase spectrum of the given function. So in this way, I can draw the magnitude spectrum and phase spectrum of the given functions. Okay. So if you have for any function, for any given function, you can draw the magnitude spectrum and phase spectrum. First, you need the equation of x of omega. First, you have to find out the Fourier transform. Okay, that Fourier transform is the summation of real and imaginary. Generally, if imaginary is 0, it will have only real part. If real is 0, it has only imaginary part. Both are present, then we have both real and imaginary parts. For that, first, for the finding the magnitude, what do have to go for? We have to go for the formula square root of real part square plus imaginary part square. Okay, and then find the phase angle. We have to go for the formula tan inverse of imaginary part by real part. By using these two formulas, I can find out the magnitude as well as phase. Okay. Now, using those magnitude value and phase value, I can draw the magnitude spectra and phase spectra. So this is magnitude spectra and phase spectra for the given unit impulse function. Okay. Now I will ask you one question. Okay. Can anyone tell me what is the Fourier transform of del of t minus t naught? Can anyone tell me what is the Fourier transform of del of t minus t naught? I need the Fourier transform of that one. Del of t minus t naught. Can anyone tell me? Yeah, that's right. Simple. How can you get that value? Simply. So here I have to find out the Fourier transform of this one. Fourier transform of del of t minus t naught. That is, our given signal is del of t minus t naught. Now the formula will convert to, what will be the formula? X of omega. X of omega will be equal to integral minus infinity to plus infinity. Our signal x of t equal to del of t minus t naught into e power minus j omega t dt. E power minus j omega t dt. Okay. So this is the formula for finding the Fourier transform of del of t minus t naught. And now you can say this del of t minus t naught will have the value only at t equal to t naught. Why? Because substitute t equal to t naught. T naught minus t naught, that is 0. So del of 0 equal to 1. That means generally we know the unit impulse function. Del function is having a value only at t equal to 0. But here the given as t minus t naught. That means the value inside the bracket should be 0. For that, we have to go for the value of t as t naught. You substitute t naught in place of t. So t naught minus t naught, that is 0. So del of 0 equal to 1. If I substitute a value other than t naught in place of t, if I substitute a value other than t naught in place of t, for that that value minus t naught will not be equal to 0. It will give some other value. It will not be equal to 0. So del of anything except 0 is 0. Del of anything, del of 9, del of 50, del of 55, what it may be, that value will be equal to 0. Okay, we have only the value of the unit impulse function as 1, only a del of 0. So here, whenever our t will be equal to t naught, t is equal to t naught, the value inside the bracket will be equal to 0. So del of 0 equal to 1. For all the values, where this value is not equal to 0, the function value is 0. The function value is 0. For that, I have to take here the value of t as a t naught. The value of t as t naught. So substitute t naught here. What happens? Del of t naught minus t naught into e power minus j omega t naught. Omega t naught. That means except t naught for any other value of t. So in place of t, if you not substitute the t naught, if you take any other value, the value inside the brackets is not equal to 0. That is del of some value. So that del of some value is equal to 0. So 0 into anything is 0. Integral of 0 is 0. So we have to consider only the value where the value inside the bracket should be 0. That is possible only when t equal to t naught. So from minus infinity to plus infinity, in the range of minus infinity to plus infinity, I will take the value of only t naught. For all the remaining values of t, this value should be 0. 0 into anything is 0. Integral of 0 is 0. So I won't consider all the remaining values. I will consider only the one value. That is, the value of t will be equal to t naught. So t equal to t naught. That is del of t naught minus t naught into e power minus j omega t naught. Omega t naught. That will be equal to del of t naught minus t naught. Del of 0 into e power minus j omega t naught. That will be del of 0 is 1. Del of 0 equal to 1. 1 into e power minus j omega naught. E power minus j omega naught. So final answer for this one will be equal to e power minus j omega t naught. E power minus j omega t naught. Simply del of 0 into e power minus j omega t naught. That will be equal to del of 0 is 1. 1 into e power minus j omega t naught. That will be equal to e power minus j omega t naught. So finally what we got? The Fourier transform of del of t minus t naught will be equal to e power minus j omega t naught. So for this the Fourier transform x of omega will be equal to, for this function, that will be equal to e power minus j omega t naught. Minus j omega t naught. Clear? So this is the first function, that is unit impulse function. So I had taken the unit impulse function. For that I had gone for the Fourier transform, and then I gone for the magnitude spectrum and phase spectrum of this unit impulse function. And finally I asked you a question, that is, what is the Fourier transform of del of t minus t naught? Del of t minus t naught. For that I got the answer as e power minus j omega t naught. So the Fourier transform of del of t minus t naught is nothing but e power minus j omega t naught. Now I'll go for the second function, that is single sided real exponential function. So the second one is single sided real exponential function. A single sided real exponential function. Okay, so the single sided real exponential function is represented nothing but as e power minus at into u of t. This is our single sided real exponential function. Okay, so simply they are given x of t as e power minus at u of t. They are given like this. So for this I have to find out the Fourier transform. So to find out the Fourier transform, I need a formula of Fourier transform, and I need the definition of u of t. Here u of t is unit step function. U of t is unit step function. Very, very important. So what is the value of the u of t? So we all know that u of t will be equal to u of t will be equal to 1 will be equal to 1 for t greater than or equal to 0 greater than or equal to 0 and the u of t equal to 0 for a t less than 0 t less than 0. So for all values of t which are greater than 0 or equal to 0, the value of u of t is 1, and for all the values of t which are less than 0, the value of u of t is 0. Okay, so we have to keep this in mind. Why? Because in that formula we have the ranges from minus infinity to plus infinity. So there I can limit those values by using this function. Okay, so we all know the function of this u of t. So definition, from the definition of the unit step function, I know u of t equal to 1 for t greater than or equal to 0 and u of t equal to 0 for t less than 0. Now go for a Fourier transform of the given signal, that single sided real exponential function. So what will be the Fourier transform? We all know the formula of Fourier transform, that is x of omega will be equal to integral of minus infinity to infinity x of t e power minus j omega t dt. So here the signal x of t will be equal to e power minus at into u of t. So this can be written as x of omega will be equal to integral minus infinity to infinity e power minus at u of t e power minus j omega t dt. Okay, see, the values are from minus infinity to plus infinity. The t values are from minus infinity to plus infinity. So there is no need to consider all the values, because from minus infinity to 0, the value of u of t is 0. 0 into anything is 0 and the integral of 0 is 0. So there is no need to consider the values from 0 to minus infinity to 0 in this integral. That means this u of t is having the value of 1 for t greater than or equal to 0. That means we have to consider the limits right from 0 to infinity, because for all the remaining values the u of t is 0. So 0 to anything is 0, integral of 0 is 0. So we don't need to consider that value. That means simply you can write this as integral limits. It will start from 0 to infinity, because less than 0 the value of this one will be equal to, if the t value is less than this one, so if t value is less than 0, u of t equal to 0, 0 to anything is 0. No need to consider all this. So integral 0 to infinity e to the power of minus at, and in 0 to infinity the value of u of t is 1. The value of u of t is 1 for t greater than 0 or equal to 0. That is from 0 to infinity. For all these values, the value of u of t will be equal to 1 into e power minus j omega t dt. That will be equal to, simply we can write integral 0 to infinity e power minus at into e power minus j omega t dt. Yeah, that will be equal to integral 0 to infinity e power minus x into e power minus 5. So we have to go for e power minus x minus 5. I can take the minus as common. Then what I will get? E power minus of x plus y. In the same way, this also we can write as integral e power minus at minus j omega t dt. Minus at minus j omega t dt. So x of omega will be equal to, this one will be equal to, what happens? Integral 0 to infinity e power, see here in the both I can take the minus as common and t as common. So what happens? Minus of a plus j omega into t dt, omega into t dt, minus of a plus j omega into t dt. Okay, now what is the formula for e power minus 2t? So what is the integral of e power minus 2t? E power minus 2t divided by minus 2. Integral of e power minus 2t, e power minus 2t by minus 2. So in the same way, what is the integral of this one? So integral of this one will be equal to the function e power minus of a plus j omega into t divided by minus of a plus j omega, minus of a plus j omega. So the limits are from 0 to infinity. The limits are from 0 to infinity. Now that will be equal to substitute the limits. So what happens? E power, substitute infinity in place of t. So infinity into anything is infinity. Infinity into anything is infinity. So the value will be equal to e power minus infinity by minus of a plus j omega minus substitute 0. 0 into anything is 0, or simply you can write e power minus 0 divided by minus of a plus j omega, minus of a plus j omega. Okay. Now finally the x of omega will be equal to e power minus infinity. How can you write like e power minus infinity? So we all know e power minus infinity equal to 1 by e power infinity. That will be equal to e power infinity. Infinity is infinity. So 1 by infinity. So 1 by infinity is nothing but 0. So the value of this one is 0. So x of omega equal to 0 by minus of a plus j omega. Okay. Next, minus of minus will become as plus. And e power minus 0. Simply e power minus 0. 1 by e power 0. E power 0 is 1. That is 1 by 1. So 1 by 1 is 1. So here the value is 1. Divided by minus of minus already becomes as plus. So I can simply write a plus j omega. So 0 by anything is 0. So the value of this one is 0. So finally x of omega will be equal to 1 by a plus j omega. That is the Fourier transform of this single-sided real exponential function e power minus at into u of t is nothing but 1 by a plus j omega. Or simply you can write like this: Fourier transform of e power minus at into u of t will be equal to 1 by a plus j omega. Okay, you can denote like this, or you can represent the Fourier transform pair as e power minus at into u of t will have a Fourier transform. That means you have to write a line with 2 arrows on both sides, and on the top of the line you have to write ft. That is, this function will have a Fourier transform 1 by a plus j omega. So you can represent in any one of this way, either this way or this way. Okay. So this is how to find out the Fourier transform of the single-sided real exponential function. Now see, if you want to draw the spectrum, that is magnitude spectrum and phase spectrum of this one. So I got x of omega as this one. What I have to get? I need magnitude of x of omega and phase of x of omega. So for that I need separate real part and imaginary part. Here this is 1 by a plus j omega. I have to rewrite this equation in the format real part plus j into some imaginary part. We have to write like this. For this I have to go for the rationalizing of this one. Okay. Now I will go for finding the magnitude spectrum and phase spectrum of this one. Okay, that is we have to find out the value of mod of x of omega and phase of x of omega. So we all know x of omega equal to 1 by a plus j omega. Okay. Now I have to find out the magnitude spectrum and phase spectrum. So for that I am multiplying this equation with a minus j omega, both numerator and denominator. So I am multiplying with a minus j omega, numerator and denominator. So for this, for the numerator I am multiplying with a minus j omega. In the same way, I am multiplying the denominator with a minus j omega. If I multiply with the same number with numerator and denominator, there will be no change because these two will get cancelled and I get the same value. So now that will be equal to, see, what will be the value of that one? Numerator is a minus j omega and denominator a plus b into a minus b. A square minus b square, that is a square minus b means j omega whole square. Okay. Now that will be equal to a minus j omega divided by a square minus j square omega square, that will be equal to a minus j omega by a square. J square will be equal to minus 1. J square is equal to minus 1. We all know that the j square value is minus 1. So I can write minus of minus 1 into omega square, or simply minus of minus 1, that will become as plus. So we can write a minus j omega by a square plus omega square. A square plus omega square. Now I can separate this into a real part and imaginary part. So this will be separated as, how can I separate this? A by a square plus omega square minus j into omega by a square plus omega square. Clear? Okay, you can separate this. Or if I write plus here, I can write minus here. Okay, if I write plus here, I can write minus here. Okay, that is a plus jb. Okay, if you want to write like this, you can write a plus j into minus of this one. Okay, j into minus omega by a square plus omega square. Both are same. Clear? So a plus jb. Now this is the value of our x of omega. Now I got the real part and imaginary part. So from this I can find out the values of magnitude of this one and phase of this one. So first I will go for the magnitude. So the magnitude, how can I find out? So now mod of x of omega, that will be equal to square root of real part square plus imaginary part square. So square root of real parts, a by a square plus omega square whole square plus imaginary part minus omega by a square plus omega square whole square. Okay, this will be written as square root of a square by a square plus omega square whole square. So I put a square to the numerator and the denominator separately, plus minus omega square, nothing but omega square. Omega square and minus omega square both are same. Okay, so minus omega square by a square plus omega square. Okay, so that will be equal to you can write like this: a square by a square plus omega square whole square plus omega square by a square plus, here also I have to apply the square to the denominator also, that is minus omega square by a square plus omega square whole square. So a square plus omega square whole square. Now that will be equal to a square plus omega square, because denominators are same. We go for the LCM. So the LCM is same, that is a square plus omega square whole square. Okay, so the denominators are same, a square plus omega square whole square. Now I have to add the denominators, a square plus omega square. I go for the LCM of this one. See, a square plus omega square whole square means a square plus omega square into a square plus omega square. That means this one and this one will get cancelled. So finally what get root of 1 by this one, or simply 1 by root of a square plus omega square. 1 by root of a square plus omega square. So this is the value of mod of x of omega, magnitude of x of omega. In the same way, what will be the phase of x of omega? Phase of x of omega, that equal to tan inverse of imaginary part, tan inverse of imaginary part minus omega by a square plus omega square divided by real part. Real part is a by a square plus omega square. So a square plus omega square both will get cancelled. That will be equal to tan inverse of minus omega by a, or simply you can write minus tan inverse of omega by a. So this is the phase and this is the magnitude. Now using these two I can draw the magnitude spectra as well as phase spectrum of the signal. Okay, so first I will draw the given signal. I will draw the given signal, that is a single sided real exponential function, that is e power minus at into u of t. How the signal will be? See, so this is t and this is x of t. So the signal will be like this. So this is, that is nothing but e power minus at into u of t. So this is the representation of the single sided real exponential. So the single sided real exponential signal will be like this. Now for this I have to go for the magnitude spectrum. For that I have to find out the Fourier transform x of omega, and then I gone for the magnitude of that one, that is mod of x of omega. So for this I have to draw the graph. So magnitude spectrum is nothing but the plot of frequency versus the magnitude. Okay, so the graph will be like this. So here on x-axis we have the omega frequency, and on y-axis we have the mod of x of omega, and we all know the mod of x of omega will be equal to 1 by square root of a square plus omega square at omega equal to 0. So this is 0. So 1 by root of a square, so square and root cancel, so 1 by a. So the at omega equal to 0, the value will be equal to 1 by a. So in this way, if you substitute some positive values and some negative values in this, for some positive values for omega and some negative values for this omega, you can get the graph as like this. This is the shape of the graph. So for various positive values of omega, so the shape will be like this, and various negative values of omega, the shape will be like this. So this is nothing but the magnitude spectrum. Okay, magnitude spectrum. And so this is the given signal, that is single sided real exponential signal, this one, and this is magnitude spectrum. Now I go for the phase spectrum. So the phase spectrum is the plot of frequency versus the phase angle. So I have to consider the frequency omega here, and this will be 0. Okay, and here on y-axis I will have the phase of this one. So the phase of this one will be equal to minus tan inverse of omega by a. So we will have the different values. For different values of omega, I get the different values of this phase angle. If you plot all those values, the shape will be like this. Okay, this one. So this here, this value is pi by 2. In the same way, this value is minus pi by 2. Okay, so the phase angle. So the maximum value will be pi by 2 and the min value is minus pi by 2. So for different values of omega, considering the different values of omega, we will get the different values. See, if omega equal to 0, tan inverse of 0 nothing but 0. Hence the point is here. For different values of omega, a positive side, and for the different values of omega, negative side, the shape will be like this. So this is the phase of spectrum. So this is the phase spectrum. Okay. So here in this first I find out the Fourier transform of the single-sided real exponential function, and I converted that x of omega into real part plus j into imaginary part like this. So from this I find out the values of magnitude of x of omega and then phase of x of omega. Okay, so using these two I draw on the magnitude spectrum and phase spectrum. I draw the magnitude spectrum and phase spectrum. Okay, so it's simply the magnitude spectrum is a plot of frequency versus the magnitude of that x of omega. So this is the equation. In this equation, for different values of omega, I get the different values of mod of x of omega. If I plot a graph for all those values, the shape will be like this. Okay. So for your understanding, I given an example. At omega equal to 0, the value of this one will be equal to 1 by a. At omega equal to 0, the value of this one equal to 1 by a. In the same way, the phase of x of omega is nothing but minus tan inverse of omega by a. So for various values of omega, I get various values of phase angles. So if you plot the graph for all those values, the shape will be like this. The shape will be like this. Okay. Clear? Yeah. Here also, omega equal to 0. For your understanding, I have taken omega equal to 0. Tan inverse of 0 by anything, tan inverse of 0. Tan inverse of 0 is nothing but angle 0. So hence at omega equal to 0, the phase angle also 0. For different positive values, that will be like this, and for different value that will be like this. So that will be the shape of the phase spectrum graph. Okay. So in the second example, I had taken the function as a single-sided real exponential function. The shape of this single-sided real exponential function will be like this. For this, first I gone for the finding the Fourier transform, and then I find the magnitude spectrum and phase spectrum, and I draw the magnitude spectrum and phase spectrum. This is the second one. Now I will go for the third function. That is a double-sided real exponential function. The second one is single-sided real exponential function. Here the third one is double-sided real exponential function. The second one is a double-sided real exponential function. I go for the double-sided. So that is the exponential function will be on both sides. That is on the positive side and negative side. So the type of functions will be represented with e power minus a mod t e power minus a mod t. That is a double-sided real exponential function, because here all the values are real values, and this is double-sided. That is, for this case I have taken mod t. That is, t has both negative values as well as positive values, minus t and plus t. So they had given x of t as e power minus a mod t. E power minus a mod t. Now I will elaborate this one, expand this one perfectly. How can I expand? I have to separate it for negatives and positive values. So how can I write this? X of t will be equal to e power minus a into minus t for t less than or equal to 0. T less than or equal to 0, that is less than 0, that is minus negative, hence I can write as minus t, and the value of this x of t will be equal to e power minus a into plus t for t greater than or equal to 0. For t greater than or equal to 0 it is plus t, and for t less than or equal to 0 it is minus t. Okay. Now if you combine both, I will get the double-sided real exponential function. So I have to combine this both. So these two can be combined using the help of unit step functions. How we will see? See, x of t will be equal to, so this function exists for t greater than or equal to 0. So t greater than or equal to 0. What is the value of u of t? U of t equal to 1. So for t greater than or equal to 0, u of t equal to 1. So in this case, if I multiply this equation with u of t, that u of t value is 1. 1 into that 1 is same value. So there is no change in the value. Instead of writing t greater than or equal to 0, I will write u of t. Why? Because the u of t value is 0. For t less than 0. So here the value of u of t is 0. 0 into anything is 0. That means that u of t will give the values only for t greater than or equal to 0. And that value will also 1. 1 into anything is that value will come. So for this, so this should be multiplied with u of t, then there will be no change in this equation. In the same way, the above equation should be multiplied with u of minus t. We all know the equation of u of t. U of minus t equal to 1 for t less than or equal to 0. And for t greater than 0, the u of minus t value is 0. So for greater than 0, u of minus t is 0. 0 into anything is 0. So I won't get any values for t greater than 0. For u of minus t, because u of minus t exists only for t less than or equal to 0. For t less than or equal to 0, the u of minus t value equal to 1. So 1 into this value will be equal to that value. So here, instead of this I can write u of minus t. Instead of this I can write u of t. Then there will be no change, because u of t for this range value is 1. 1 into this one is this one. And in this range u of minus t is 1. 1 into this one is that value. So there will be no change. So I can add this both using the functions, unit step functions like this. See, so x of t equal to e power minus a into minus t into u of minus t, okay, plus e power minus a into t into u of plus t, okay. Simply you can write like this. That will be equal to minus of minus plus. So e power at into u of minus t plus e power minus into plus minus e power minus at into u of t. So that is our x of t. So here the value of x of t, is this one. Now I have to find out the Fourier transform. So we all know the formula of Fourier transform. So what is the formula of Fourier transform? X of omega will be equal to integral minus into infinity x of t. So here the x of t is this one. So e power at u of minus t plus e power minus at into u of t e power minus j omega t, dt. So in the formula, in the minus infinity x of t e power minus j omega t dt, I substituted x of t value as this one. Okay. Now see, this u of minus t exists. Only for t less than or equal to 0, that is minus infinity to 0. So this function is only for minus infinity to 0. Okay. Now this will be equal to integral minus infinity to 0. We have the value of this u of minus t, that will be equal to 1. So 1 into this one is e power at into, I'm directly multiplying this one. Okay, I'm separating this also in a single step. So e power at into e power minus j omega t dt plus c, from 0 to infinity the value of u of t is 1. Okay, so here I will take from 0 to infinity. I will consider this one. I won't consider this one because from 0 to infinity the value of this one is 0. 0 to anything is 0. So 0 into this one also 0. So no need to consider this one from 0 to infinity. I will consider only this one. In the same way, in the previous case also, while I am considering for u of minus t, that I had taken minus into 0. So minus into 0, this value is 1 into this one is e power 80, e power 80 into this one is e power 80 into e power minus j omega t. In that case, the value of u of t is, in that case, so minus into 0, this is 0 into anything is 0, so there is no need to write this one in the first case. So in the second case, I will write only this one, there is no need to write this one. So simply here I will get as e power minus 80, and the u of t value is 1, no need to write that one. So e power minus 80 into e power minus j omega t dt. So this is how to write this one, simplify this one. Now I need the value of x of omega, that will be equal to, see, integral minus infinity to 0, minus infinity to 0, so e power x into e power y, e power x minus y, that is e power 80 minus j omega t dt, okay, plus integral 0 to infinity, integral 0 to infinity e power, so minus x minus y, simply minus x minus y, take minus as common, so take minus as common, what will get, a plus j omega into d, and directly writing steps, okay, into dt, because in the second example I did all this, so I directly write the step dt, so that will be equal to, so here I took minus as common, so a minus j omega into 2, minus and t as minus t as common, okay. So what is the integration of this function? So the integration of this function will be equal to, so what will be the integration of this function? So here also I can take a t as common, here also I can take t as a common. So if I write one more step, integral minus infinity to 0 e power a minus j omega into t dt plus integral 0 to infinity e power minus of a plus j omega into t dt, okay. So integral of this one will be equal to, integral of this one, e power a minus j omega into t divided by a minus j omega, this is the integral, okay. The limits are minus infinity to 0, plus, what is the integral of this one, e power minus of a plus j omega into t divided by minus of a plus j omega, this is the integral, and the limits are 0 to infinity, that will be equal to, see, substitute 0 into anything is 0, so I will get e power 0 by a minus j omega minus substitute this one, what happens, e power minus infinity into anything is minus infinity divided by a minus j omega, this is the first case, plus integral substitute infinity here, so e power, so infinity into anything is infinity, so I will get e power minus infinity by minus of a plus j omega minus substitute 0 here, 0 into anything is 0, so I will get e power minus 0 by minus of a plus j omega, this is the second function. See, that will be equal to e power 0 is 1, so 1 by a minus j omega, okay. So e power minus infinity, 1 by e power infinity, is infinity, 1 by infinity, that is 0, the value of this one is 0 into anything is 0, so there is no need to write this one, no need to write this 0, plus, so here also e power minus infinity, 1 by e power infinity, that is 1 by infinity, that is 0 divided by anything is 0, no need to write this one, so minus of minus plus e power minus 0, 1 by e power 0, 1 by e power 0 is 1 by 1, simply 1 by minus of minus already plus, so simply a plus j omega, so finally I got 1 by a minus j omega plus 1 by a plus j omega, 1 by a minus j omega plus 1 by a plus j omega, okay. This will be equal to, so go for LCM, that will be nothing but a minus j omega into a plus j omega, that is a square minus j omega whole square. J omega whole square, that is j square into omega square. Now in the numerator I will get a plus j omega plus a minus j omega. Okay, so minus j omega plus j omega get cancelled, that will be equal to 2a divided by j square minus omega square. So j square is minus 1, minus of minus plus, so finally I will get a square plus omega square, a square plus omega square. So the final answer for this one will be equal to, the final answer for this one is x of omega will be equal to, x of omega will be equal to 2a by a square plus omega square. 2a plus 2a by a square plus omega square. So this is the Fourier transform of the function x of t equal to e power minus a mod t. For this function, the Fourier transform x of omega will be equal to 2a by a square plus omega square. Okay, so this is how to find out the Fourier transform of a double-sided real exponential function, that is e power minus a mod t. So this way we can find out the Fourier transform. Now I am giving you some small work, that is here you have to find out the magnitude spectrum and the phase spectrum for this one. Simply the magnitude spectrum is mod of x of omega. Here we have only the real part, there is no imaginary part. There is no imaginary part. There is very easy to draw the magnitude spectrum. So here the mod of x of omega is nothing but square root of real part square plus imaginary part. There is no imaginary square. The square root of real part square is this one. Square root square cancel this one. So mod of x of omega is this value. Mod of x of omega is this value. Okay. So omega equal to 0. This one 0. Okay. 2a by a square. A square cancel. That is 2 by a. So in the previous case, in single-sided real exponential function, I got whenever omega equal to 0, I got the maximum value as the magnitude mod of x of omega as 1 by a. Here that is 2 by a. The shape is same. The shape will be same. The magnitude spectrum of a single-sided real exponential function and double-sided real exponential are same. Only the change is at omega equal to 0, the value is 1 by a. Here at omega equal to 0, the value is 2 by a. Only change that one. Okay. That with that you can get the magnitude spectrum. What about phase spectrum? There is no imaginary part, that is tan inverse of 0, that is 0. So for all values of omega, there is no phase, the phase is 0, that is 0. Okay, so you can draw the magnitude spectrum and phase spectrum. And how the signal of this double-sided, I show you the signal of single-sided, that is one side. So here we will get the signal on both sides. Here we will get the signal on both sides. Both sides. Here we get the signal as both sides like this. So this is t, this is x of t, which is nothing but this one. Okay, both sided. And if you want to get the magnitude spectrum, and if you want to get the magnitude spectrum, so the magnitude spectrum is same. Shape is same. Okay, here this value is 2 by a, and this is mod of x of omega, and this is omega, and this is 0. Okay, this one, this is the magnitude spectrum, and phase spectrum is 0 for all values of omega. For all values of omega, that is 0. Simply omega angle of x of omega 0. So this is the phase spectrum. Okay, so I already explained you how to draw this a double-sided real exponential function and the magnitude spectrum and the phase spectrum. Okay, practice that one at your home. Okay, for your better understanding. So with this I am finishing today's class. So in this class I gone for the Fourier transform of some basic functions, that is like standard signals. That is first one I gone for the unit impulse function, and then I gone for the single sided real exponential function, and then I gone for the double sided real exponential functions. For each function I shown you the signal representation and then magnitude spectrum and phase spectrum. Okay, in the next class I will go for some of the functions. Okay, some of the functions. Okay, so this is today's class. Thank you, one and all.